Unit 2C, Lesson 3, Modeling Functions to Situations. In this lesson, we're going to be given a situation, a real-life situation, and then we need to determine whether or not that is best represented by a linear equation or exponential equation. Question I want you to think about as we go through this lesson: how can you determine if a situation is best modeled by a linear function or exponential function? Okay, so we're going to go through many examples, then at the end, I'm going to want you to answer this question in your notes. So the first example, we want to determine one characteristic of all linear functions is that they change by equal factors over equal intervals, unequal factors over equal intervals, equal differences over equal intervals, or unequal differences over equal intervals. Okay, so I think the easiest way to answer this question is to look at an example. So if we looked at the linear equation y equals 2x plus 1, made a table of values, x values -2 to 2, and then the corresponding y values if we would plug those x values in. So over here, our x values are changing by the same interval, okay, which all of these are referring to. They're over equal intervals. So we want to compare what's happening to the y values. Each time they're increasing by 2, they have a common difference of 2. Okay, so these two that refer to factors aren't going to work because we're not multiplying by a value each time to get these different changes. The change in between the pattern is we're adding 2. We have a common difference, an equal difference over an equal interval. Now to the next example, which situation could be modeled by using a linear function? So we have 4 different examples. The first one, a bank account balance that grows at a rate of 5% per year compounded annually, a population of bacteria that doubles every 4.5 hours, the cost of cell phone service that charges a base amount plus 20 cents per minute, the concentration of medicine in a person's body that decays by a factor of 1/3 every hour. Of these 4, 3 of them are referring to the same type of function that we talked about earlier in the year. The first one, second one, and fourth one are all referring to exponential functions. A bank account, if we're trying to determine how much is in there, if it has a common rate or that rate of 5% per year, that's exponential. A population of bacteria that doubles, that's exponential. The concentration of medicine that has a decay factor, that's exponential. The only one that is going to be linear is the cost of a cell phone service that charges a base amount plus 20 cents per minute. And we could easily write this in slope-intercept form. If we knew the base amount, that would be our y-intercept, and then we have our slope, our rate of 20 cents per minute. So the correct choice in this case would be number 3. To the third example, which situation is not a linear function? So the first one, a gym charges a membership fee of $10 down and $10 per month. A cab company charges $2.50 initially and $3 per mile. A restaurant employee earns $12.50 per hour. A $12,000 car depreciates 15% per year. So 3 of these should be easy to recognize as linear functions because they all can be written in slope-intercept form very easily. The first one, if we wanted to write a linear equation for this, we have our y-intercept, the initial amount, and our rate, our slope of $10 per month. The second one, you have your y-intercept of $2.50, and you have your rate of $3 per mile. And then the third one, you do not have a y-intercept, a base salary, but you have the rate of $12.50 per hour. So the one that is not a linear function is the fourth one. You have a $12,000 car, it depreciates by 15% per year. That's our exponential decay model. So the correct choice is number 4. And to the fourth example, which scenario represents exponential growth? So the first one, a water tank is filled at a rate of 2 gallons per minute. A vine grows 6 inches every week. A species of fly doubles its population every month during the summer. A car increases its distance from a garage as it travels at a constant speed of 25 miles per hour. So the first one, a water tank is filled at a rate of 2 gallons per minute. That's a linear function. It has that constant rate that's going to increase by the same difference over every minute. Second one, a vine grows 6 inches every week. Same thing. We could create a linear equation to model the growth of that vine, be y equals 6x, x representing the number of weeks. The third one, a species of fly doubles its population every month during the summer. We should start recognizing by now that that is going to be exponential growth. Okay, that's the same as when we had bacteria doubling. It would go into the same type of equation. That general equation would be y equals a times 2 raised to the x power. A representing the initial amount of the population, 2 is our growth factor, it's doubling, and then x representing the number of months during the course of the summer. The fourth one, a car increases its distance from a garage as it travels at a constant speed of 25 miles per hour. Okay, you learned that in physical science, and earlier this year, that's just a linear equation relating the distance to the rate and the time, linear equation. So the correct choice is number 3. Now that we've gone through some of those examples, I want you to go back and answer this question. How can you determine if a situation is best modeled by a linear function or exponential function? Think about some of the key words we're looking at and the behavior of those situations that allowed us to determine whether or not it was linear or exponential.